So, today we're diving into something that's kind of like a mathematical superpower. It's the ability to prove a statement is true for an infinite number of cases, without actually having to check every single one. It's called mathematical induction, and honestly, it's one of the most powerful tools for proving something with absolute certainty.
All right, so let's start with the big problem that induction was even invented to solve. Imagine you found a cool pattern, maybe a formula that seems to work for the number 1, and for 2, and for 100. How can you be 100% certain it works for every single positive integer, all the way out to infinity? How do you prove something forever?
So how do you do it? Just check them all? No way. It's literally impossible. You could spend your entire life checking the first billion cases, or even the first trillion, and you'd still have an infinite number left to go. For instance, there's a famous formula for adding up the first n numbers. 1 plus 2 plus 3 all the way to n equals n times n plus 1 all divided by 2. It works for 1, it works for 10, it works for 1,000. But how do we know it'll work for a number with a billion digits? Yeah, we're going to need a much smarter way to do this than just checking one by one.
And this quote from the mathematician Alfred North Whitehead really nails what this is all about. You know, the real magic of math isn't just about finding one specific answer. It's about proving things that are true for any case, without having to list them all out. It's about finding these universal truths, and that's exactly the kind of tool we need if we want to tackle infinity.
Okay, so how on earth do you solve an infinite problem with a finite proof? Well, the key is this really beautiful, super intuitive idea that you already get, a chain reaction. And the best way to visualize it is with the classic domino analogy.
Go ahead, just picture this in your head for a second. A line of dominoes, all set up perfectly. And this line just stretches out further than you can see, over the horizon, literally forever. There is no last domino.
So really think about that. You can't walk to the end to see if the last one falls, because there is no end. What would you need to be sure of, right here at the very beginning, to know with total certainty that every single domino in that infinite line is going to fall?
Well, it turns out you only need to be sure about two things. That's it. Just two. First, you have to actually start the chain reaction. You've got to push that very first domino. And second, you have to make sure the chain reaction keeps going, that any domino that falls is guaranteed to hit the next one. If you can prove those two things, you know for a fact the whole infinite line will topple over.
Okay, so let's take that super simple idea and translate it into the formal language of a mathematical proof. You'll see that the core logic, those two crucial steps, they stay exactly the same.
Instead of a physical push knocking over dominoes, what we're really doing is using logical implication to prove the next case in a sequence. We are literally building a chain reaction of truth.
So step 1 is what we call the base step, and this is our starting line. All we have to do is prove our statement works for the very first case, which is usually n equals 1. This is almost always the easy part, but it's so important. This is us pushing that first domino. So for that sum formula, we test n equals 1. The sum is just 1. The formula gives us 1 times 1 plus 1 divided by 2, which is also 1. 1 equals 1. Boom. The first domino is down.
All right, now for the part that can feel a little weird, almost like a magic trick. It's called the inductive hypothesis. Here's the thing. We don't prove anything in this step. Instead, we just assume that our statement is true for some random number, and we'll just call it k. This k could be 5, it could be 5 million, doesn't matter. It's like pointing to a random domino, way down the line, and just saying, okay, let's just pretend for a second that this one falls. For our formula, we assume that 1 plus 2 plus all the way to k really does equal k times k plus 1 over 2. This assumption sets us up for the final, most powerful move.
And this is the real engine of the proof. This is the inductive step. Our whole goal here is to prove a connection. We use our assumption about k as a tool to show that if the statement is true for that random domino k, then it absolutely must be true for the very next one, k plus 1. This is us proving the dominoes are spaced perfectly. For our formula, we'd look at the sum up to k plus 1. We can split that into the sum up to k plus k plus 1. And hey, we already have an assumption about what the sum up to k is. We plug that assumption in, do a little bit of algebra, and we prove that the formula also works for k plus 1. What we've just done is prove that if any one domino falls, it absolutely positively guarantees that the very next one falls too.
See how that works? You absolutely need both of those pieces, the base step and the inductive step, working together. If you're missing even one of them, the whole proof just falls apart, just like our domino chain would.
So what happens if you skip one? Well, let's look. On one side, what if you have no base step? Well, you've proven the link, the dominoes are all spaced perfectly, but you never actually push the first one. The chain reaction is all set to go, but it never, ever starts. And on the other side, what if you have no inductive step? Well, you prove the base case, you push that first domino over, but then there's a big gap somewhere in the line. The process starts, but it stops dead in its tracks. You need both to make that infinite chain happen.
So why does any of this matter? I mean, it's a cool logic puzzle, but what's the point? Well, it's because this technique allows us to build things with total certainty, especially in fields that rely on logic that has to repeat over and over again.
And that's really the big takeaway here. Induction takes a problem that seems infinitely complex, proving something forever, and shrinks it down to just two manageable steps, proving a start and proving a link. This isn't about being pretty sure. It's basically a machine that creates absolute certainty, forever.
And believe it or not, this has some huge real-world applications. In computer science, it's used all the time to prove that an algorithm will work correctly, no matter how big the input is. When you sort a list of files on your computer, you want to know for sure that algorithm is going to work if you have 10 files or 10 billion files. Induction is the tool that can prove it. And of course, it's fundamental in all sorts of advanced mathematics.
And that, right there, is the beautiful power of induction. You take two finite provable steps, a start and a link, and you use them to build a logical bridge all the way to infinity. It's a gorgeous idea that guarantees a chain reaction will just keep going forever. Which kind of makes you wonder, outside of math, if you could prove a start and a link for anything, what's one positive chain reaction you'd want to kick off in the world? Thanks for watching.